Hello viewers, welcome back to my channel. So in today's class we're going to continue with our lesson on dimension analysis. But today we will consider the second application of dimension analysis, which include deriving formulas using dimension analysis. So let's consider the following examples. The first question says that the time period t on a simple pendulum depends on its length L and the acceleration due to gravity g. Using dimensional analysis to derive the formula for t. So in this case, we are asked to derive the formula for t, which is the pendulum period. We are asked to use dimensional analysis to derive the formula for the pendulum period t. So let's consider the parameters given to us. The period here, period is equals to t, and the dimension still remain t. The next one is the length L, and the dimension still remain L. Now the acceleration due to gravity, the dimension of acceleration due to gravity will be given to be Lt raised to the power of what? Of minus 2. We consider the acceleration on a straight line where your u is equals to 0. So the dimension of acceleration due to gravity will be Lt raised to the power of what? Of minus 2. Now interpreting the parameters given to us here, the question says the time period t on a simple pendulum depends on its length L and acceleration due to gravity. That is, t is directly proportional to L and g. Is directly proportional to L and g. Where proportionality sign is equals to k, and k is considered to be constant and dimensionless. K is constant and dimensionless. Now let's assume that t is equals to k, L raised to the power of a, and g raised to the power of what? Of b. T is raised to the power of 1 here. Now let's take the dimensional relationship between this expression here. Now we're going to be having t raised to the power of 1 to be equals to k. The dimension of L will be raised to the power of a, multiplied by the dimension of acceleration due to gravity will be Lt raised to the power of minus 2 raised to the power of what? Of b. Now by equating this, now we're going to be having k to be equals to dimension of L raised to the power of a, multiplied by dimension of L to be raised to the power of b, and dimension of t raised to the power of minus 2 raised to the power of what? Of b. Now we can equate this, and we're going to be having L raised to the power of a plus b. According to the product law of indices, t will be raised to the power of minus 2b. T will be raised to the power of minus 2b. Now by equating the power on the left hand side and right hand side, the power of t on the left hand side is 1 to be equals to the power of t on the right hand side is minus 2b. So equating the power of b will be equals to minus 1 over 2. B will be equals to minus 1 over 2. Equating the power of L, the power of L on the left hand side is equals to what? To 0, and the power of L on the right hand side is given to be a plus b. On the right hand side is given to be a plus b. Now equating this now, our value for b here is minus 1 over 2 equals to what? To 0. You can continue by saying a equals to what? 1 over 2. Now let's substitute the power that we just derived. Now recall that t is equal to k L. Now my value for a is what? 1 over 2 multiplied by acceleration due to gravity g. The power is what? Minus 1 over 2. Minus 1 over 2. Now I can re-express this as square root of L. Square root of L multiplied by. Now recall from negative index law of indices, that is, this g can be re-expressed as what? 1 over g raised to the power of 2, which we can express as square root of 1 over g. square root of 1 over g. Now since both dimensions are having square roots, we can express this and say square root of L times 1 will give me L over g. Therefore, t is equals to k square root of L over g. We've just derived the equation for the period t. Equation derived using dimensional analysis. Now, the second example says that the velocity v depends on distance s and time t. Use dimensional analysis to prove the equation. Now, let's consider the parameters given to us. Velocity. And velocity simply means displacement over time taken. And the dimension of velocity is L t raised to the power of what? Of minus 1. Now, for the distance, the dimension of distance s still remain L. The dimension of the time taken, that's time t still remain t. That's the dimension of the time t. Now, by interpreting this expression, v is directly proportional to s multiplied by t. V is directly proportional to s multiplied by what? By t. Now, let the proportionality sign be equals to k, where k is constant and dimensionless. K is constant and dimensionless. Therefore, we can say v to be equals to k s t. Now, taking the dimension of the equation, recall that the dimension of velocity is what? Is L t raised to the power of what? Of minus 1 to be equals to k, L, and what? And t. Now, considering the power of each parameters given here, that is, our v now can be expressed as k, L raised to the power of a multiplied by t raised to the power of what? Of b. By equating the power of this dimension here, we can express it as L t raised to the power of minus 1 to be equals to k L raised to the power of a multiplied by t raised to the power of what? Of b. So by comparing the power of the quantity on both sides, the power of L, which is a, will be equals to 1. And the power of t, which is b, will be equals to minus 1. So by substituting the power a and b, so k will be equals to L raised to the power of 1 and t raised to the power of what? Of minus 1. Therefore, velocity v is equals to L multiplied by t raised to the power of minus 1. Now we can express this as L multiplied by the inverse of t will be 1 over t. The inverse of t will be 1 over t, of which we can say L multiplied by what? By 1 over t. Therefore, v will be equals to L over t. Equation proved. Equation derived. And velocity is equals to displacement over time taken. That is, velocity is equals to displacement over time taken. Equation proved. Let's consider the third example. The third example says that if force F depends on mass m and acceleration a, use dimensional analysis to prove that F equals to ma. Now let's consider the parameters given to us here. By considering the parameters, F, which is a force F, is equals to mass times acceleration, and the dimension of force is given to be ml t raised to the power of minus 2. Now the next parameter given here is mass. Mass still remain m, and the dimension is what? Is m, is a fundamental quantity. The next parameter here is acceleration. Let's consider this. Acceleration. Now, acceleration A has the dimension of lt raised to the power of minus 2. Has the dimension of lt raised to the power of what? Of minus 2. Now, given that f is directly proportional to m multiplied by a, we are asked to prove this. Now, let proportionality sign be equals to k, where k is what? Is constant and dimensionless. Now, the dimension of the equation f is given to be m lt raised to the power of minus 2 equals to m multiplied by the dimension of acceleration is lt raised to the power of minus 2. So, expressing the dimensional relationship of the two quantities given to us, we can proceed by considering the power of the quantity on the right hand side. This one is regarded as what? As the dimension on the right hand side, and this is the dimension on the left hand side. So let's assume that the exponent of the quantity on the right hand side is x and y, or you can say a and b. That is m lt raised to the power of minus 2 is equals to m raised to the power of x multiplied by a raised to the power of y. That's the exponent of the dimension on the right hand side. So we can proceed by saying m lt raised to the power of minus 2 is equals to m raised to the power of x. Now the dimension of acceleration now will be lt raised to the power of minus 2 raised to the power of y. So we can open the brackets by saying mx multiplied by l raised to the power of y multiplied by t raised to the power of 2y. By comparing the power, or the exponents on the right hand side and the left hand side, the power for m, which is x, will be equals to 1 because m is having what? The power of 1 on the left hand side. Now the power of l on the left hand side, which is equals to y, is 1. Now the power of t on the left hand side, which is equals to what? Y as well, on the left hand side is minus 2. And on the right hand side as well is also equals to minus 2. Pardon me, we have minus 2 here. Is also equals to minus 2y. So if we divide both sides by minus 2, y will be equals to 1. So this implies that y is equals to 1 for t. So we can proceed and say f is equals to the constant m, which has the power of what? Of 1, multiplied by the acceleration, also having the power of what? Of 1. Hence proved. Hence f is equals to ma, where k is constant. K is what? Is constant. Where k is constant, hence prove that force is equals to mass times acceleration. So now let's consider the fourth example. The first example says that if kinetic energy E depends on mass m and velocity v, show that E is equals to kmv square. E is equals to kmv square. Now we can consider the parameters, that is kinetic energy is equals to, let's take it as E, and the dimension of energy is given to be ml raised to the power of 2 t raised to the power of minus 2. For mass, the dimension of mass still remain m, that is the dimension of mass. And for velocity v, the dimension of velocity v is considered to be LT raised to the power of minus 1, that is displacement over time taken. Therefore, interpreting the expression given to us here says that kinetic energy E, I will take it as E, is directly proportional to M multiplied by V. Let the proportionality sign be equals to what? K, and K is what? Is constant and dimensionless. Is constant and dimensionless. So we can say E now is equals to mv. Let's take the dimension of energy, which is ml raised to the power of 2, t raised to the power of minus 2, is equals to m multiplied by the dimension of velocity, which is l t raised to the power of minus 1. Okay, let's assume the power of the dimension on the right hand side is having x and y. That is, m is raised to the power of x, and the second expression, which is the velocity, is having lt raised to the power of minus 1 raised to the power of what? Of y. Now we can proceed by saying m raised to the power of x multiplied by the dimension of l raised to the power of y, t raised to the power of minus y. You can close the bracket again. So by comparing power of the dimensions on both left and the right hand side, considering m with the power of x, m is having exponent of 1, and for l with the power of y is having 2 on the left hand side. Now for t, which is having the power of minus 2 at the left hand side, will also be equals to 2. This implies that minus 2 will also be equals to what? 2. The power of what? Of 2 on the right hand side. This implies that energy E will be equals to K m raised to the power of 1 multiplied by V raised to the power of 2. Therefore, E will be equals to K m V square. Hence proof that energy E is equals to mv square. So if you like my video, kindly subscribe to my YouTube channel, share with friends, and press the notification button to receive every new video I'm going to be dropping on this channel. See you in the next class. Thank you. Bye.